button now. So, I mean, for the record of the video that is being recorded now, this is the discussion session concerning the course, and from this point on, the live lectures will be recorded and put in the Moodle platform for those who are not able to attend them. Okay, but please do not use this as a way for not showing up in these lectures, because I do need your feedback in these lectures. If this sort of a procedure will result in a shorter participation to the live lectures, I will interrupt it, because in this case, the very point of the lectures, getting a feedback from you guys, will be missing. Okay, so with this mutual gentleman's agreement, so to say, let me proceed in discussing. Let me proceed in discussing the exercise, and to do that, I will share my screen, my iPad AirPlay or a whiteboard. I think I will do the iPad AirPlay for this time. Okay. Now you're gonna be seeing soon my screen. Let's see. Yes. Okay, let me go here and open a note. Okay, so I don't quite remember the details, but let's try to work it out. So the idea is that at time t0, I'm experiencing a potential that is this potential, and I am in a ground state of this potential. So at time t equals to t0, my wave function psi state is in the ground state of the harmonic oscillator. So now, in principle, to be completely pedantic, I'm thinking of a physical system that can be in principle realized. And the way I was thinking is that I have a one-dimensional system that is confined in a box. Maybe there's a, you know, kind of a very hard wall interaction here that in reality, they are smooth, but very steep. So if I were to plot this potential and look it for a large distance, it would look like this, not like this. Okay? However, I'm assuming that this change in behavior occurs at a distance that is sufficiently large for the wave function of the ground state, which I will plot here, to be so small that it's completely insensitive to this detail. Okay? So effectively, under these circumstances, my problem can be formulated mathematically in a much simpler terms, is that at time t0, my potential, my system is in this state, and the Hamiltonian until that point was the harmonic oscillator Hamiltonian. And at time t0, for greater than t0, the system changes Hamiltonian. So precisely at time t0, if you want, the Hamiltonian goes from the harmonic oscillator Hamiltonian to a different Hamiltonian, let's call it H0, which is the Hamiltonian for a square well with size L. So I have relaxed, I have taken away the harmonic trap. And what is nice about this exercise is that it is in principle possible to realize it physically with trapped atoms, for instance. if you, as soon as the restrictions for the COVID pandemic emergency are released, you can walk up the physics department and go and talk to the people in the Bose-Einstein condensation group, and for instance, talk to Alessandro, sorry, talk to Professor Ferrari, who is an expert of experimentalist with, manipulation of atoms. And he will teach you how you can interpolate, you can trap atoms into harmonic traps and into other types of traps, and you can really remove the harmonic trap all of a sudden. And using magnetic fields, typically these traps are based on magnetic fields. And so you can actually play with this tool and really realize the physical systems I'm here using as an exercise. So this is not as abstract as it looks like. You can even realize effectively one-dimensional system by confining the motion on the other direction to be strictly confined. So it takes a lot of energy to excite motion in the transverse direction. So the system is always in the ground state of the transverse motion. And so the system behaves effectively as one dimension. Okay? So this all premise to say it's not a crazy situation. And first of all, what we would like to know is what is the probability? Question number one is what is the probability of observing the ground state energy of the harmonic oscillator? Sorry, what is the probability of observing any energy? Okay, this is not the right notation. This is the right notation. So what is the probability of any of the possible energy outcomes of the system? Now, this is a, okay, fine. Okay, I mean, I'm not sure I should say all this detail. Okay. But yes, in principle, for the moment the system, okay, let me say that after we go to the answer of this question. Anyone has an idea? Federica, please do not answer now. Let's have a discussion with the other members in the room, okay? So in order to address this question, go back onto the general rules of quantum mechanics and tell me if you have an idea of how to address this question. You should have if you don't have your notes with you, you can go on my webpage and look at chapter 4, where I have put the general rules of quantum mechanics for making predictions. So in general, given an observable associated with an operator, what are the outcomes of possible measurement of that operator in a physical system?
the eigenvalues of the operator.
Okay, so can we translate this piece of information to the present problem?
I mean,
What is the quantity we want to measure now? What is the quantity being
the
measured?
energy.
Okay, so what is the operator associated with the energy?
Hamiltonian.
The Hamiltonian.
Okay, so first thing we learned, the operator in this case is the Hamiltonian. Okay? So what do we want to find out? We want to find the probability of observing the operator, the eigenvalue, the eth eigenvalue, which in this case is the probability of observing the eth energy. So first of all, for this discussion, it appears that the possible outcome of an experiment are the energies of what? What Hamiltonian?
The Hamiltonian of the harmonic oscillator, quantum harmonic oscillator.
Right, the Hamiltonian of the quantum harmonic oscillator. Okay? So, are you sure? Because if that was the case,
Maybe
the answer would be the probability is only E, the only outcome would be the ground state of the Hamiltonian. So if I have my system in the ground state of the Hamiltonian operator, and then I ask you make a measurement, knowing that is in the ground state of the Hamiltonian operator, the only state, the only eigenvalue we get. So if my system is in this Hamiltonian with this potential, and I tell you that it is in the ground state of the Hamiltonian operator, the only outcome would be the ground state of the Hamiltonian operator with probability 1. Do you agree? Because my system is in the ground state of this Hamiltonian. It's an eigenstate of the operator, so there's no dispersion, there's no stochastic behavior. It's an eigenstate of the operator. If I measure the energy of that operator, I'm going to get the corresponding eigenvalue all the times. I repeat the measurements. So I get the ground state of the Hamiltonian operator with probability 1. Okay?
Because I know I am in that state, so I can say, okay, I'm right there.
And that is an eigenstate of the Hamiltonian. Now, what I do now, I change the Hamiltonian. And almost immediately, I perform the measurement. Now, this adverb, almost, is the reason I was hesitating to speak some times ago. So if you unwind this lecture, you notice that I have been hesitating to speak because there's a subtleties here, but let me worry about that later. So this word almost is a placeholder for a later discussion that I'm going to have with you. So it's just there for saying, I'm going to tell you something about this immediately, but wait for it, okay? So soon after I take away my trap, the Hamiltonian of the system is changed into a new Hamiltonian. So the state of the system has not changed because I changed the Hamiltonian. I didn't touch the particle. Okay? But I changed the Hamiltonian. Everybody is with me on this. If you're not with me on this, speak up. So given the fact that I have removed the harmonic trap, my Hamiltonian now is the H0 Hamiltonian. So now I go back. So what I have here is H0. Right? O is H0. So the question I'm asking you is, what are the possible outcomes of energy measurements? They are the eigenstates of what Hamiltonian? The eigenvalues of what Hamiltonian? Question.
The Hamiltonian made up by the potential energy of the oscillator and the box. It's like a union, but okay.
I have removed the trap. Once again, let me draw a diagram. You discover what I mean. Okay? So this is time. This is T0. Okay? Up to this time, the Hamiltonian was this. So if actually, technically, this is the potential. Okay? Kinetic energy doesn't change. Okay? Very good. At time T0, from time T0 on, the potential energy has become this. In this very moment here. Okay? Because I have removed the trap.
Okay.
And at time, sometimes almost immediately after T0, here I make a measurement. See, this is the almost, which will come to later. Okay, so for the sake of now, think it's immediately after. Okay? There will be a minimal time lag that I want to discuss with you in a moment. Okay? But for the sake of the exercise, is immediately after. So now I make a measurement. The measurement will resolve what eigenstates? So the eigenstates of the Hamiltonian, but now the Hamiltonian, which is the Hamiltonian of what?
Of the box, because I changed my potential.
So
okay.
The possible energies will be the eigenstates of the E0, H0 Hamiltonian. Do we have an agreement on this?
Yeah.
Okay, so how do I compute these Hamiltonians? The corresponding probability. Let's be specific. How do I compute the probability of E0 not, where this is box and this is ground state? Okay, so the index above, suffix, is for remind me that this is the first eigenvalue of the box Hamiltonian. And the index downstairs is just for sake of definedness that we are looking at the ground state.
Maybe it's the energy level corresponding to the kinetic energy associated with the ground state. of the harmonic track.
So remember the general rules. I'm going to erase this board. Okay, is everybody okay with this board? So remember, what does the general rule say? The probability of observing the ith eigenvalue of my operator is given by the corresponding eigenstates projected on my state, square modulus. Do we agree? Now, all we have to do now is to fit in the right things. So OI are now the ground states energy of the box Hamiltonian. The corresponding state is psi naught, the ground state of the box Hamiltonian. Okay? So, at the same time, the state at time where I'm making a measurement, right, at time t naught plus delta t, which is this almost immediately. So let me remove this and not worry about this, okay, for a moment. So the state at time t naught when I'm making the measurement is the ground state of the harmonic oscillator Hamiltonian, right? So what should I compute to get this? You only have to apply the rule. Somebody tell me.
The inner product of the eigenvalue and the wave function at time t0.
So let me, this is the wave function. This is the eigenstate associated with the corresponding eigenvalue. So this is the state such that h naught psi naught naught equals h naught naught psi naught naught. So I want to get this probability of this eigenvalue. I take the inner product with the corresponding eigenstate. Is this clear? That's the rule. That's what the rule means. Very good. I'm losing every, so I on my right part of the screen, I don't see the students I was interacting with. Is he still in online? I don't see it. Let's see. Yes, I see you now. Just to make sure that, you know, I'm answering to somebody. Okay. So are you guys with me on this? You're not with me, or you are? Who's not with me at this point? So all we have agreed on is that to get this probability, I need to compute the overlap, technically speaking, it's called the overlap, between the ground state of the box and the ground state of the harmonic oscillator, and then take the square modulus of the result. Okay? Now, as usual, when I compute these things, remember, I want to do v dot w. I want to make, in order to compute things, I need to choose a representation. Okay? And in coordinate representation, this would be the integral from minus LF to LF of psi naught naught star of x, psi HO naught of x. So if you wonder why it is so, I've discussed this in the lecture, but let me remind you, while the left-hand side here of this equation is equal to the right-hand side of this equation. And to do that, I use the analogy with vectors in normal linear algebra. I want to take the inner product to vector. Let me call it V and W. V plays the role of this, and W plays the role of this. For instance, it's an analogy, right? So this is a three-dimensional vector space, and the other one is an infinite dimensional vector space. So they're not exact equalities, just the analogy we always used to build and discuss Hilbert spaces, right? So what I do, I write the following. I project onto my basis, which essentially specifies the representation of my vector space. And this will give me V times E1 times W1 plus V times E2 times W2 times V times E3. And in turn, this is V1 W1 plus V2 W2 plus V3 W3. And you can collect on this into I, VI, WI. Right? You're well familiar with this trivial derivation. Now, in this particular case, the role played by the versor. So V is associated with psi H naught O. W is associated with psi naught no. And I'm interested in W times V. And then EI are the eigenstates of position operator. So the components VI are actually the wave function. And the components WI are the complex conjugate of the wave function. Okay? Therefore, the right-hand side. If you're not completely familiar with this, go over it, go over this lecture, and go over the previous lecture until you become familiar with this. 90% of the mathematical formalism of quantum mechanics is encoded in these simple linear algebra manipulations, but you have to become familiar with that. And by the way, you understand linear algebra better if you do. So So that's why you should do it. Okay? Good. So let's do this. Let me erase here. Now, I don't have my notes with me. Somebody has the notes. So I'd like you to tell me exactly the structure of the ground state wave function of the harmonic oscillator, please. I know it's a Gaussian. I know it contains x squared. Please tell me what is in the normalization and here in the variance of this Gaussian. Can anybody help me? I can search it in Wikipedia, but I was thinking you would have this information. So quantum harmonic oscillator. Okay, here's the answer. So if I go and look at it, it's going to be 1 to the, so it's going to be 1 mw divided by h bar pi to the 1/4, and that's going to be e to the minus m over twice h bar omega x squared. Okay, you guys are frozen. Oh no, okay, you're moving again. Now I need the wave function of the ground state for the square box, right? Now, if I look at it, I get Okay, so this is the information. The Eigen energy is given by this, the 0-point energy, if you want, and the corresponding wave function is this. So the probability of observing this value of energy, if I make a measurement, is given by, I'm going to write it in red now, down here, integral from minus L half to L half dx root 2 over L m omega h bar pi to the 1/4, and then e to the minus m x squared divided by 2h bar times cosine of x pi over L. Now it looks like very complicated. It probably is very complicated, but it can make it a little bit easier if you want. We're going to make room. Now remember, we are assuming that the wave function of the harmonic oscillator was decayed sufficiently fast for not to experience the wall, remember? So it means that I can take this integral from minus infinity to plus infinity. It doesn't really make a difference, because whatever happens from L half on, or near L half, is completely irrelevant, because there's a large exponent here killing it, exponential function killing it. So this is very much similar to the, say, 2 over L m omega over h bar pi to the 1/4, and then the integral from minus infinity to plus infinity in dx of e to the minus mx squared divided by 2h bar cosine of x pi over L. Now you might choose to do this approximation or not. I chose to do that because I'm under the impression that this is an integral that might be solvable. So I'm going to look on Mathematica to see if this is an integral that is solvable. The worst comes to the worst, you can always use any numerical package to do that. Okay? And I wasn't asking you to get the right number out. I was just asking you to write this. This is called reducing a problem to quadrature, which means that basically you have everything with you except one final integral to evaluate. Okay? When your problem is reduced to the problem of evaluating an integral, but you can use either numerics or, I don't know, whatever it takes, exact solutions to do that, that's called reducing a problem to quadrature. So what I'm doing now as I speak, I'm trying to see whether this is actually an analytically calculable integral, or it is not. There's a missing omega here, obviously. Sorry. There was a missing omega here, I guess. Let me check the omega. Where was the omega missing here? Yeah, it's in here. There's an omega upstairs. Okay. Yep, it's an analytical solution. I was right. The final result is actually, without my glasses, I can't see anything anymore. Sign of aging. Its result is actually equal to root of 2 over L m omega over h pi to the 1/4. I'm copying this times the result of the integral, that is h bar over root of 2 pi divided by root of h bar m omega times exponent h bar pi squared divided by 2L squared m omega. Now, I really don't care if you don't find this final complicated formula. Okay? Because, you know, we've been lucky that this integral could be solved, and we did the approximation of letting the integral going from minus infinity to plus infinity. These are technicalities that come with a little bit of experience, and I don't expect you to be able to guess that or to have a program that solves the integral. But I do expect you to understand that you have to do this integral to get the answer. Okay?
So, excuse me, Professor.
Sure.
Just to make a recap. We calculated the probability of being in the ground state energy of the box just in the delta T meter potential, and then I take out the oscillator potential and I put the box potential in that little amount of time, right?
Now, the probability of finding a system to find the ground state of the box soon after I've replaced the potential from being a harmonic oscillator to the box.
Okay. So after that little delta T time.
Okay, the little delta T time you can forget for now. I discuss it now. So in the mathematical problem, I have a potential at in time T naught. I change the potential and make the measurement. Okay. And I ask, what kind of result can I get? And one of these results is the eigenstate of the new potential. And the corresponding probability of getting this result is what we computed. Okay?
All right, thank you.
Now it's time to say, why did I wait a little bit of delta T? Because, you know, this is really, really, really what quantum mechanics doesn't say. Because there's something mysterious of quantum mechanics. And I confess to you, I'm gonna come clean. I think very few people, if any in the world, have an understanding of what I'm about to say. But I certainly don't. And the point is the following: quantum mechanics doesn't tell you what happens during the collapse of the wave function. Doesn't tell you what happens when the wave function suddenly realizes that the underlying Hamiltonian is changed. Okay? So there is some transit. So if I were really making the measurement, the moment I press suppose I have a button which changes the Hamiltonian from harmonic oscillator and to square box. That's my first button. And I have another button where when I press it, I make the measurement. Okay? Ideal situation. Now, if I'm really pressing the two buttons at the same time, so in the very same instant, I'm changing the Hamiltonian and making a measurement. Okay? All of a sudden, the system changes, and the new ground states are those of the new Hamiltonian, right? But how on earth can nature know that the Hamiltonian is changed if I'm making the measurement exactly when I'm changing it? How does the system know that the underlying Hamiltonian has changed if it's changing exactly when I'm making a measurement? That's a subtlety, right? Do you appreciate this problem? So I have to wait a little bit for the system to realize that the underlying physics has changed, right? But if I wait too much, my system will evolve according to the time evolution of the new Hamiltonian. So it will go into whatever combination of eigenstates of the Hamiltonian. Look at the lecture of the time evolution operator. So I have to wait the least time possible and make the measurement. So that's why I said almost immediately. And if you want, I could elaborate what I mean by almost. I don't see this in books. My personal guess is that the least time scale you need to wait, delta t, will be of this order. But that's my own physical intuition between the ground states of the harmonic oscillator and the ground state of the new system you're measuring. But that's my intuition based on how things should go. But I don't ask you to understand all this. And I just want to say, if I were to be very rigorous, I cannot press the two buttons at the same time because the system must have some time to realize that the underlying Hamiltonian has changed. You see? So stated differently, it's like if I'm saying, suppose, okay, let's go into, suppose I'm an alien, and the aliens in my example have discovered a technology to cancel gravity. You know, they can put gravity to 0. I saw a cartoon for my child yesterday where this was happening. Okay, so that's why I have this example. Now, suppose I'm asking you, at time 0, the aliens cancel gravity. What is the acceleration of any body in proximity of the Earth? You know, so I'm in a similar situation. Here is g, here is 0. This is when the alien cancels gravity. And now, if I perform the measurement slightly earlier than this, I will measure g. If I measure it slightly after, I will measure 0. But there will be a transient time where the gravity is going to 0. Right, because the machine is not operating in 0 time, will operate in a finite time, right? So I have to allow this to happen. And the same happens with quantum measurements. It will take the system a finite time to realize the underlying Hamiltonian has changed. And during this finite time, the wave function is evolving with it. Okay? So if you were to do this very sophisticated, you would have interpolate the two Hamiltonians and see what happens along the transition from one Hamiltonian to the other. It's a mess. For this exercise, this is good enough, okay? I just wanted to tell you why I mean almost immediately after. But that's really subtlety. I don't have to worry about that. I just wanted to be thorough and precise in my presentation, okay?
Should I calculate the probability as a function of the state? Because how can I, my question is that how can I be sure that the probability in the ground state is the highest after the trap is removed?
Oh. So in principle, I can give you pedantic into inverted commas. It's not pedantic. A rigorous answer, or sort of the answer of a guy who's been in the field for long enough. So I expect you to give the first answer, not the second, okay? So the first answer is, I should calculate all of them, and the largest is whatever is the largest probability, okay? Because all I can do is to take all different probabilities and whoever is the largest, whatever is the largest, that's the largest probability event, period. So it's not nothing deep here. Just do the calculation for everything and until you're done, okay? Now, clearly, if your two potentials look similar, so namely, if the Gaussian has a spread that is not very different from the spread of the other, so a situation in which they are not very different, not very similar would be one like this, right? Where the typical size of the harmonic oscillator ground state is decoupled from L. Because that's a size in which a harmonic oscillator is like this, right? But as long as the two potential are not too dissimilar, like in this case, then I have basically the overlap with this, this is the cosine, the ground state of this Hamiltonian, while the green one is the ground state of this Hamiltonian, right? So this is going, the overlap means take the product of this times this, and then take the integral. Clearly, the more similar two functions are, the largest will be the integral, because it's an inner product. If I have the inner product of a function with itself, it will be largest. Now, if I look at the excited states, they are small when the ground state is large. You see? This is where the ground state of one is large, and this is the first excited state. So I would expect, in principle, to the overlap to be largest for the ground states. That's the answer of somebody who's been in the field for some time. But you're not supposed to have that insight because you have not been in the field for some time. Okay? Did I answer to you?
I understand it now. I was just thinking maybe we could evaluate some expression based on the wave function, but
yeah, you can. In principle, each probability is a different. Sorry. Oh, don't remember whichever index is the ground state. Suppose this is the ground state. So this will be n here. These are all the probabilities, right? But n is equal to 0, 1, blah, blah, blah. And so each of these corresponds to a different integral, where in one you substitute the ground state of the box, in two you substitute in 0 the ground state, in 1 the first excited state, and blah, 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 blah. So you get a different integral for each of these different probabilities. And then you get all these numbers. And the largest one is the most probable. And if you ask me, my guess would be it's going to look like this. Here is the index that tells you which excited state you are. And this is the probability of that measurement, and it's going to be like this. Zero, 1, 2. It's going to be an exponential fall down as a function of n. The probability of observing the first excited state is going to be smaller than the probability of observing the ground state, and so on and so forth. So what I expect is Pn plus 1 going to be smaller than Pn. So the most probable would be, of course, P0. But that's what I expect. For being in the field for a long time, you should do the calculations. In principle, it can be done. If you have access to Mathematica, Maple, or whatever online code, you can play around with this. Now, having done this exercise thoroughly, I'm going to ask you a very closely related exercise, and you should be able to solve it. Okay? This is exercise for you now. Okay? And I will not discuss this in lecture unless you cannot solve it and you want me to discuss it in one of the next Wednesdays, okay? Here comes the exercise. My Hamiltonian, my potential is the square box potential. And it's remaining square box for all time. But what's happening is I have a particle and this particle somehow at time 0 splits, decays in two particles. Let's call it A and B at time t0. And let's suppose A is invisible, meaning that I cannot measure its position with whatever instrument I'm using. I can only measure this. And let's suppose that MA is equal to MB equal to M half. This is particle M. So in other words, particle A splits into two particles at time 0 of equal mass, and only one of these two particles can be measured. The other one, it's there, but I cannot see it with my instrument. For instance, if I use some kind of electric device and this and particle A is electrically chargeless, I'll never be able to see it. Clear? There are particles like that. For instance, neutrinos. They are neutral, as the word says. So you can never measure them with a standard canalimeter for electrons, so to say. Okay? So the probability, what is the probability of the energy of particle B at time t0? Say to find what are the typical possible outcome of measuring the energy of particle B, and what are the corresponding probability. So same problem, but rather than changing the potential, I am basically changing the mass of my particle from M to M half. So the problem can be formulated like this. At time 0, my mass of the detectable particle is reduced by 2. Find the probability. Okay? Now, physically, you can realize this, imagining that a particle is decaying in 2 and one of them is invisible. That's the physical setup you have in mind. But from a mathematical point of view, you can say, at time t, I'm changing the particle and getting half of the mass of the particle. At time t0. What is the probability? What are the possible outcome of my measurement, and what are the corresponding probability? I want you to think about this and try to come with an answer next Wednesday. Let's do this. You know, talk among yourselves, think it through, and try to come with an answer next Wednesday. That's my assignment. If you understand the problem that we've done today, you should be able to understand this problem. Because conceptual is very, very, very close, but not identical. So remember, this is the kind of situation where they give you a problem that is almost identical to the one that we discussed, but not exactly identical. So if you only understood the problem and you learn the problem that I give you by heart, and you cannot answer this, you haven't understood the problem. You think you have understood the problem. You have learned the lesson, and it's an entirely different story. Remember the discussion of having an impression of understanding things. If you can repeat the lecture that I just gave you with everything clean, but cannot answer this question, it means that you have learned the lesson, but haven't understood the physics that is in the lesson. Okay, I don't expect you to have understood it now because, you know, it takes time to process things. But that's what it means to learn physics, rather than to look at physics being told or being able to repeat a lesson about physics. Okay? So challenge yourself. I'm happy to help. If you need to, I will deliver a little piece of information if you get stuck. Even before Wednesday, write it on the chat. If you think you need a hint, I'll give a hint and not help you through. and do come with an answer next Wednesday. Okay? Doesn't matter if it's not the correct answer, push yourself to do that. It's important that you guys go through this effort while you can still ask questions. Because if you want to go over it at the end when I'm not going to be around anymore, it's likely that you come to the exams that you think are incredibly well prepared because you can repeat every single word I say, but you eventually can fall on questions like this, okay? I mean, don't mean to scare you. I just want to, set the bar of what it means physical understanding. And not everyone has to take 30 in the final grade. I mean, it's fine to get 26, 27, 28. So don't be like, if you're not very much into getting this, it's okay. You're going to pass the exams anyway. But for 30, I mean, people are being able to do these kind of things. Okay. Good. Now, we almost exhausted the time we have for the lecture. So I will not go too much into asking questions about the hydrogen atom. Maybe we leave that to the next lecture. What do you guys think?
Yeah, I think it's better.
It's quite a lot to process here. But guys, it's okay. I don't expect you to find this easy. It's okay if it's tough. It's quantum mechanics. It's not supposed to be easy. It's supposed to be tough. It must not be impossible. That's all I'm saying. Okay? And the rest is on you. Okay? Are there more questions on this? Well, if not, we can call it a day. And I post this on Moodle as soon as this is finished, okay? Okay. Bye-bye, guys.
Bye-bye.
Thank you. Bye.
Thank you.